All right, today we're diving into a classic computer science showdown, Kruskal versus Prim. Now, these are two legendary algorithms that both solve the exact same problem, but trust me, the way they go about it is completely different. So let's break down how they work and see who comes out on top.
Okay, let's make this real. Imagine you're in charge. You've got a bunch of company offices scattered all over a city, and your job is to connect every single one with high-speed fiber optic cables. Now here's the catch. Every possible connection has a price tag. So the big question is, how do you link up every office either directly or indirectly for the absolute minimum cost? That's the puzzle we need to solve. So that perfect cheapest network blueprint, well, it has a name. It's called a minimum spanning tree, or MST for short. Let's break that down. It's a tree because it connects everything without any wasteful, redundant loops, no cycles. And it's minimum because the total price tag for all the cables is the absolute lowest you can possibly get. This is the holy grail that both of our algorithms are chasing.
First up, let's meet our first contender, Kruskal's algorithm. The best way to think about Kruskal is as the global planner. This algorithm wants to see the entire map, every single possible connection, before it even thinks about laying the first cable. It takes this huge, top-down, big-picture approach.
So here's Kruskal's game plan. It starts by taking every single potential connection and sorting them all in a big list, from the cheapest to the most expensive. Then it just starts going down that list, one by one. It looks at the next cheapest connection and asks a simple question. Does this link up two parts of my network that weren't connected before? If yes, great, we build it. If adding it would create a loop, nope, we just skip it and move on. It's really as simple as that.
Let's just walk through that one more time. Step one, and this is the most important part for Kruskal's, is to sort all the possible edges by their cost. Then, you just go through that sorted list and you greedily add the cheapest edge you can find, but only if it doesn't form a cycle. You just keep doing this until, boom, every single office is connected into one big network. But you might be wondering, how does it know if it's about to create a cycle? Well, that's where it pulls out its secret weapon, a super clever data structure called Union Find. Just think of it like this. It keeps track of different teams or groups of connected offices. Before it adds a new cable, it asks Union Find, hey, are these two offices already on the same team? If the answer is yes, then adding that cable would create a loop, so it's a no-go. It is an incredibly fast way to keep things from getting loopy. Okay, and now for our second contender, Prim's algorithm. And this one has a totally different personality. If Kruskal's was the global planner with the big map, Prim's is the local explorer. It doesn't care about the whole map at the start. Instead, it just picks one spot and starts carefully, cautiously growing its network one step at a time. The way Prim's works is you can literally start in any city you want. From there, you look at all the roads leading out from the territory you've already connected. Out of all those options, you always pick the single cheapest road that leads to a brand new, unexplored city. You build that road, your connected territory gets a little bigger, and you just do it all over again. Yeah, the process is actually pretty elegant. You start with just one office. You scan all the connections on your frontier, the ones that lead to places you haven't connected yet. You find the absolute cheapest one, add it to your growing tree, and now your frontier is bigger. To keep track of that cheapest edge really efficiently, it uses a tool called a priority queue. And you just repeat and repeat and repeat until every last office is part of your network. Okay, but wait. How can this local explorer approach be sure it's finding the global minimum? It seems almost too simple, right? Well, it works because of a fundamental mathematical guarantee called the cut property. Here's the idea. Imagine you could slice your graph into any two pieces, any two groups of offices. The cut property guarantees that the single cheapest cable that crosses that slice has to be part of the final minimum spanning tree. So at every step, Prim's is basically making a cut between what it's already built and, well, everything else. And it's always safely picking that guaranteed cheapest edge. So there you have it. We've got Kruskal, the global planner, and Prim, the local explorer. They're both greedy, they both get the right answer, but they could not be more different in their approach. So the big question is, when you're actually faced with this problem, which one do you pick? Let's put them head-to-head and find out. And this table really sums it all up. You can see the perspective. Kruskal is global, thinking in terms of connecting different forests together. Prim's is local, just growing a single tree. Their core action is different. Kruskal sorts everything first, Prim's grows from a point. Now, look at the time complexity. Often it's the same, but that last row is where the magic happens. Kruskal's really shines on sparse graphs. Think maps with lots of cities, but not a ton of roads.
Prim's, on the other hand, tends to win out on dense graphs, where pretty much everything is connected to everything else.
And this chart right here shows you exactly why. On a really dense graph, we're talking one where the number of edges, E, is getting close to the number of vertices, V, squared. That massive sorting job Kruskal has to do at the beginning becomes a major bottleneck. But a particular implementation of Prim's can just chew through that dense graph in V squared time, which makes it the undisputed champion for these superconnected networks. All right, theory's great, but let's get practical. Let's talk about the field guide, the stuff you absolutely have to know if this comes up in a coding interview, or if you're actually going to use this stuff in the real world. Okay, time to bust some common myths. First up, do these algorithms work with negative weights? Absolutely. That's a myth. Negative weights are totally fine. Both algorithms can handle them. Myth number 2, Kruskal's breaks if the graph is in disconnected pieces. Nope, false again. It'll just find a minimum spanning forest, which is just the best tree for each separate island in your graph. And the biggest myth of all, Prim's is always faster. No way. As we've seen, it totally depends on how dense your graph is. So if you're heading into an interview, here's your cheat sheet. 1, know your data structures. You got to connect union find with Kruskal and priority queues with Prim. 2, be able to explain why they're correct. Talk about the cut property for Prim and the avoiding cycles rule for Kruskal. 3, think about the edge cases. What happens with disconnected graphs or parallel edges? And finally, 4, show you're a pro by mentioning the different complexities for Prims. It shows a deeper understanding. So at the end of the day, we have the global planner versus the local explorer. 2 completely different philosophies, yet they both find that one perfect optimal solution. And these ideas are everywhere. Power grids, the internet, logistics networks, they all use these core principles. Which kind of makes you think, doesn't it? The very network that's delivering this to you right now, which algorithm do you think had a hand in building it?